demonstrations on electromagnetic induction. Current is induced in a loop if the magnetic flux through the loop changes. The magnetic flux changes if one of three things happens. One of those is if the magnetic field, the external magnetic field at the position of the loop changes. Another is if the area of the loop itself changes. And the third is if the orientation of the external magnetic field in the loop changes. In this demonstration, we have a solenoid, which is some red wire wrapped around a core, and that solenoid is connected to a direct current power supply. There's a switch that allows me to connect or disconnect the circuit, make it an open or closed circuit. Around the solenoid, there's some black wire that is connected to a galvanometer. So the black wire is not connected to any power supply at all. If current goes through the black wire, it'll show up on the galvanometer. The galvanometer indicates whether or not current is flowing through the black wire and in what direction the current is flowing. You can see that pointer or needle on the galvanometer move in just a minute. So what I do is I close the switch or open the switch, and as I do either one, you see the galvanometer needle jump just a little bit. When I close the switch, the needle goes in one direction. When I open the switch, it goes in the other direction. When I close the switch, the current through the solenoid is going from nothing to something, causing a magnetic field in here that goes from nothing to something, and that magnetic flux through the black wire is again going from nothing to something. That causes the needle to go in one direction. When I open the switch, the current in the solenoid is going from something to nothing. The magnetic field it creates is going from something to nothing, and thus the magnetic flux through the black wire is going from something to nothing, causing a current in the opposite direction. If I hold the switch down, so there's a steady current through the solenoid, there's no change in the magnetic flux, and so there's no current induced in the black wire. I have here another solenoid. This one is connected directly just to a galvanometer. There's no power supply involved at all. The galvanometer again will show whether or not there's current going through the solenoid and in what direction. I have also a bar magnet. Here's the north pole of the bar magnet. When I bring the bar magnet into the solenoid, the needle goes in one direction. When I pull it out, the needle goes in the other direction. When I bring the magnet into the solenoid, that increases the magnetic field at the position of the solenoid, thus increasing the magnetic flux. That increase in magnetic flux causes the current to go in one direction. When I pull the magnet out, the magnetic field at the position of the solenoid decreases. That decreases the magnetic flux and causes the current to go in the other direction. When I leave the magnet still in the solenoid, you'll notice that the galvanometer indicates no current is flowing. There is a magnetic field there, but there's no change in the magnetic flux. Since there's no change in the magnetic flux, there's no induced current. Here I have two aluminum rings and a magnet. Remember that aluminum is not attracted to magnets, so it's not a magnetic material. This ring is complete, and this ring has a slit in it. You can see the slit here. First I'll pass the magnet, first I'll get the ring steady. Then I'll pass the magnet through the complete aluminum ring. And if I do that in a rhythmic fashion, you see a considerable swing of the magnet. What's happening is, as the north pole of this magnet approaches the ring, the magnetic field at the position of the ring changes, and thus the magnetic flux through the ring changes. That change in magnetic flux induces a current in the ring. That current in the ring causes its own magnetic field, and these two magnetic fields repel each other, and the ring starts to swing. If I try that with the other ring, the one with the slit in it, you notice that that ring does not start swinging. I still have a changing magnetic flux at the position of the ring, but I don't have a complete circuit, so no current can flow through the ring, so it cannot set up its own magnetic field to repel the other magnetic field. Here I have an electromagnet that's plugged into the wall, so it has alternating current in it. So the current keeps changing direction, so the magnetic field it creates keeps changing direction, and so we have a changing magnetic flux through this aluminum ring that's on the device. So if right now the electricity is not turned on, so the ring isn't doing anything interesting, but soon it will. When the electricity is turned on, you'll have a changing magnetic flux in this aluminum ring that will cause a current in the ring that will set up its own magnetic field. The magnetic field from the electromagnet and the magnetic field from the ring will oppose each other, and the ring pops off. I have an aluminum tube and two weights. Remember that the aluminum is not a magnetic material, so magnets would not be attracted to it. If I drop one of the weights down the tube, it falls out the bottom just as you would expect. But if I drop the other weight down the tube, it takes a lot longer for the weight to fall out. So the question is why? Well, as you might suspect, the second weight is a magnet. Consider one point in the aluminum tube. If the magnet approaches that point, it's going to cause a change in flux at that point, as we've discussed before. That change in flux causes a current in the tube. That current causes a magnetic field. So now we have an upward force on the magnet caused by this magnetic field that's induced in the aluminum tube. That process occurs all the way down the tube, so there's always an upward force on the magnet as it goes down the tube, and it takes longer for it to fall out. It doesn't matter if it's the north pole of the magnet that comes in or the south pole of the magnet that comes in, that repelling force is still going to occur.